continuing in 12.2, circles and polar coordinates, got a couple of little things here. If I give you r equals a, that's just a circle centered at 0, 0 with a radius of a, absolute value. If I give you r equals 2a sine theta, that's a circle that has a center at 0a, and its radius is also square root of a. But if I give it to you as 2a cosine theta, now my center is at a0 with a radius of absolute value of a. So my graphs, this one would just be here, where this is a. This guy would appear above with a radius of a. And this one appears on the right side with a radius of a. So now we want to graph. Example 4 wants us to graph r equals 1 plus the sine of theta. So this one's not a circle. And I know we can let our calculator do it, but we should also know how to do it by hand. So if I was graphing this by hand, I would have to plot a bunch of dots. Now what you do is you pick theta and you figure out r. So I'm going to pick ones that make sense. I'm going to pick 0, obviously. And then I'm thinking maybe I'll go by pi over 4s. That might be sufficient. This would then be pi. And I have to go all the way to 2 pi. So if I keep on going here, 5, 6, this is 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. So now, the sine of 0 is 0 plus 1 is 1. The sine, I don't like pi over 4. Square root of 2 over 2 plus 1. That might not be nice numbers. Let's not do pi over 4s. Let's do, pi over 6 would be better. Because the sine of pi over 6 is a half, and so I would get 3 halves. Sine of pi over 2 is 1, so I would get 2. Not this one. Let's do 5 pi over 6. That's going to put me in the second quadrant with a reference angle of pi over 6. Sine of pi over 6 is still a half, and it's positive in the second quadrant, so I still get 3 over 2. Sine of pi is 0, so I get 1. Nope, don't like that one either. What do I want this time? 7 pi over 6 gives me a reference angle. 7 pi over 6 is in the third quadrant with a reference angle of pi over 6. The sign is negative in the third quadrant, so it's going to be 1 minus a half, which gives me a half. That one is going to be, the sine of 3 pi over 2 is negative 1, so plus 1 is 0. Not this guy. 11 pi over 6 would be in the fourth quadrant. Reference angle is pi over 6. It's going to be negative, so it's negative 1 half, plus the 1 is 1 half. And then finally back around, 2 pi is going to be the same as 0. So when I graph this one, okay, we're going to go out a radius of 1, and I'm going to let this be 1 right out here. A radius of 1, an angle of 0, so that's right here. The next one is a radius of 3 halves, so it's going to go further out, and pi over 6, which is about here. This is the line I'm looking at. I'm not going to draw any more lines after that, but that's my 3 halves. Now pi over 2 is straight up and down, and I have to go out 2. So up there. It's going to be a little distorted, I think. I think this point needs to go a little further out, but we'll be okay. The next one is 5 pi over 6, and it's going to go out at 1.5, so about here. What should be even with that one? Let's see, about there. And then we have pi, which is right here, going out 1. Then we have 3 pi over 2, and we get 0. Oh, I skipped. 7 pi over 6, and we get a half. Okay, so it's going to be about here. And then 11 pi over 6 and a half. It's going to be here. And again, this is what I'm looking at. This is 11 pi over 6. This is half of the unit. So if I graph this in the order that I found them, it goes... Yeah, it's really lopsided. I'm not doing a good job with this one. It's called a cardioid. It kind of resembles a heart. And as we change numbers on it, it changes how big it is. All right, the next thing we talk about is symmetry on polar equations. And if you're being symmetric on the x-axis, it would happen whenever r theta is on the curve, r negative theta would be on the curve. So that would make sense because one's going clockwise, one's going counterclockwise, one's going clockwise, the same difference. So one dot would be here, the other dot would be there. Makes them symmetric on the x-axis. If we're talking about symmetry about the y-axis, that happens when you have r comma theta and you have r comma pi minus theta, which would be the same thing as writing negative r negative theta. So symmetry on the y-axis happens when both of them change to negatives. And then symmetry about the origin. Again, if you start with r theta, it's symmetric on the origin whenever you end up with negative r comma theta, which actually is the same thing as r comma theta plus pi. So symmetry on the x, you change the theta. Symmetry on the y, you change both. And symmetry on the origin, change the r. Example 6 wants us to graph r equals 3 sine of 2 theta. Graphs that have things like this, these are called roses. And if you graph enough of these, you'll notice a few things about them. The first thing is that you get twice as, if it's an even number in front of the theta, you will get twice as many petals as the number. So in this case, it's a 2, so we're going to get 4 petals. If it's an odd number, you get that many petals. So if it said 3 sine of 3 theta, there would only be 3 petals. So this guy right here determines the number of petals. Even, twice the petals. Odd, just that number. Okay, the number in front tells you how long the leaf is, the petal is. Petal length. So the book does it a little bit different than I do, but it's still going to come out the same graph. I'm still going to plot by hand r and theta, starting at 0 and going all the way around to 2 pi. The question is, where should I do each of these? It appears that I should use pi over 4, because then 2 times it would be pi over 2. And then I'm going to use pi over 2 and 3 pi over 4 and pi, and I'm going to run out of room. 5 pi over 4, 3 pi over 2, and 2 pi. Oh, I missed one. 7 pi over 4, 7 pi over 4, and then finally 2 pi, which won't fit there, but it'll be the same as 0. So sticking in 0, sine is 2 times 0 is 0, times 3 is still 0. Pi over 4 times 2 is pi over 2. Sine of pi over 2 is 1, times 3 is 3. Put pi over 2 in there, times 2 is pi. Sine of pi is 0, times 3 is 0. 3 pi over 4 turns into 3 pi over 2. The sine of that is negative 1, so I get negative 3. Put pi in there, it's the sine of 2 pi, which is 0, times 3 is 0. 5 pi over 4 times 2 is 5 pi over 2. 5 pi over 2 is the same as pi over 2. The sine of pi over 2 is 1, so this is going to be 3. 3 pi over 2 times 2 is 3 pi. That's the same as pi. The sine of pi is 0. And then 7 pi over 4 times 2 is 7 pi over 2, which is the same as 6 pi over 2. Pi over 2. Is that right? Yeah. No. 7 pi over 4 times 2 is 7 pi over 2. That's 3.5 pi's. So that's the same as 3 pi over 2, which is negative 1 times 3 is negative 3. And then back around to 0. So if I graph this, 0, 0 is the starting point. That's also known as the pole. Pi over 4 out a length of 3. Pi over 4 is a 45-degree angle out a length of 3. I'm going to put it out here. And then pi over 2 is back to 0. So you have to pay attention to what's going on here. 3 pi over 4 is negative 3. Okay, so 3 pi over 4 is right here, but I have to go negative 3, so it's going to put it over here. So far what I've got is this guy comes out, catches that, comes back in, and now it's heading down here. So what's next? Now it goes back to 0. And now I'm doing 5 pi over 4, which is in the third quadrant, out 3, so it's out here. So it's going to continue coming down, catching this guy, going back to 0, and the other guy is at 7 pi over 4, which is in the fourth quadrant, but negative 3, so it puts it in the second quadrant out here. So it's going to continue through to make the 4 petals. Now, what's not happening is it's not going like this. Doop, 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 doop. Oops, that was a really bad one. But what it's doing is it's coming out, finishing that, going this way, doing that guy, and then doing, it's a smooth curve. So follow the order it's doing the petals in. It does this petal first, then it does this petal, then it goes over here and does the third petal, and then it does the fourth petal.